Alright, Math 111. Today we're going to talk about Section 8.4, entitled Quadratic Functions and their Graphs. Alright, we've already talked about Section 5.9 and 8.4, where let me write this down, in Sections 5.9 and 8.2, I should say, we were asked to solve equations that might look something like this. X squared plus 3x plus 2 equals 0. In other words, degree 2 polynomial equations. This is a degree 2 equation. I misspelled it, hang on. A degree 2 equation is also known as a quadratic equation in the evolution of the genre. So when I say degree 2, I often prefer the expression degree 2. That's also referred to as quadratic in the textbook. Okay? Alright. We know how to solve these. We solve these by factoring or by the quadratic formula. But you'll notice we are always talking about reducing things to the form where you've got a quadratic expression, a degree 2 expression equaling 0. Well, what if we relax that idea that the expression has to be 0? What if x squared plus 3x plus 2, instead of equaling 0, let's say it equals some other variable called y? And the solution set for this expression takes on infinitely many values. If y can be any value, not just 0, we'll have infinitely many pairwise solutions that will establish some sort of pattern in the xy plane. All right, we are going to graph equations of this type because we cannot list the solution set. The best we can do is graph some points of the solution set and hope to recognize a pattern in the xy plane. So that's where we're headed here today. We are here to graph expressions that look like this. y equals ax squared plus bx plus c. Alright, well, let's start out with the simplest possible degree 2 function. Let's start out with y equals x squared. If I ask you to graph this degree 2 quadratic function, well, it's a quadratic with a equals 1 and b and c both equal to 0. Now let's make a table of values, and hopefully I'll pick some nice representative values, and if I plot them I'll see some pattern. If x is minus 3, y is going to be 9. If x is minus 2, y is 4. If x is 0, y is 0. If x is 2, y is 4. If x is positive 3, y is 9. And we could keep playing this game forever. Well, the idea here is to stop and smell the roses at some point and see if we can establish a pattern emerging. Alright, let me do the best I can to graph this freehand. Alright. If x is minus 3, y is positive 9. I'll put it up here. If x is minus 2, y is positive 4. I'll put it here. If x is 0, y is 0. If x is 2, y is 4. We'll see the values repeating. If x is positive 3, y is 9. And I think you can see what's happening here. If we graph the very simple quadratic function y equals x squared, I get what we call a parabola. I'll make the dots big here. Bear with me, I'm doing the best I can freehand. So this is the graph of the quadratic function y equals x squared, and of course we get a parabola, as you probably all know. Alright, and it turns out graphs of anything of the form y equals ax squared plus bx plus c will always be a parabola. Let me write that down. Graph of anything that takes on this form is a parabola in the xy plane. Alright, now we got all kinds of parabolas. We've got tall, skinny parabolas that might open down. We've got short, fat parabolas that might open up. Every parabola has what we call an axis of symmetry. And a vertex. Now, of course, the vertex is the intersection of the axis of symmetry and the parabola itself. If you've got a parabolic type equation, if your lead coefficient is positive, in other words, the coefficient of the highest degree term, if that's positive, that will imply your parabola is concave up. And that means it bends up left to right. It turns up, opens up left to right. If your lead coefficient is negative, that implies your parabola is concave down. That means it opens down left to right. It turns down left to right. Okay? Alright, I claim that if we play our cards right, we can graph a parabola efficiently with as few as 3 points. Right? Write that down. Claim. We can graph a parabola with 3 points. We'll get all the action, we'll get the vertex, we'll get the axis of symmetry in our window. We'll get a nice picture of what's going on if we pick those 3 points with a little finesse. There's 3 steps to this process, and I'll describe them here. Step 1 is to find the axis of symmetry. Now, as you may know, the axis of symmetry is a vertical line found according to this formula, where x equals minus b over 2a. Of course, that's assuming that the parabolic expression is in standard form. Step 2. Once you know the axis of symmetry, it's an easy matter to find the vertex, as we'll see. And step 3 is to find 2 symmetric points. And there is some freedom as how to find those symmetric points depending on what type of problem situation you're in. Alright, so I claim with this information, with the axis of symmetry, with the vertex, and with 2 symmetric points, we'll basically be able to get a good picture of the parabola with all the action in our window. Let's do an example. Let's say we're going to graph y equals x squared plus 2x minus 3. Alright, what I'm going to do is try to graph this, in the xy plane as we go along here. Right, give me a minute. I'm doing the best I can. Can't really use a ruler very well in the... Hang on a minute. Try to use a ruler. It's very difficult because the tablet is pressure sensitive, so if I put a ruler on the pad, it messes things up. That didn't work either. Hang with me here. Not too bad. So there is my X and Y coordinate axes. And I'm going to graph this parabola as I go along with this three-step process. Step 1. Find the axis of symmetry. Well, the axis of symmetry is the vertical line x equals minus b over 2a. Well, b here is 2 and a is 1, so this reduces to the vertical line x equals minus 2. That is going to be, x equals minus 1, right? Let me check that. X equals minus 1 will be my axis of symmetry. So I'll put that here as easily as I can. Let me get another color and graph the axis of symmetry as a dotted line so we don't confuse it with the parabola itself, okay? Alright, there. X equals minus 1 is my axis of symmetry, okay? Alright, now step 2 is to find the vertex. Well, the vertex occurs on the axis of symmetry, hence the x-coordinate of the vertex must be -1. Well, my goal is to find then the y value of the vertex, and I can find that very easily by plugging x equals -1 into my original parabolic equation. So I'll just sub in -1 for x in the parabola equation and solve for y. Y equals -1 squared is 1, plus 2 times -1 is -2, and -3. So y equals 1, -2, -3 is -4. So we see when x is -1 on this parabola, y has to be -4. I'm going to go ahead and erase that work because I'm going to need that space to do step 3. So let me put our results here. My vertex has the coordinates -1, 4. So when x is -1, y is -4. So I will graph that point and label this point with its coordinates. The vertex occurs at the point -1, -4. Now step 3. We've got to find two symmetric points. Well, in the first few examples, our two symmetric points will be our X-intercepts. Basically, I want 2 points that determine the width of the parabola. All right, so I could, in this case, find the X-intercepts. There may be trouble later on with this. We'll talk about that in a later example. All right, to find the X-intercepts, I let y equals 0 and solve for x. And if I plug in y equals 0 into my original equation, I see I get a degree 2 equation, a quadratic equation that I can easily solve for x, much like we did in section 5.9. Alright, so if I factor this polynomial expression, I think x plus 3 times x minus 1 will do it. So I get two solutions for my x-intercepts, x equals -3 or x equals 1. So I will now graph those x-intercepts. Right, at -1, 2, 3, -3 will put me here, and 0, 1, x equals 1 will put me here. So the points -3, 0 and 1, 0 represent my x-intercepts of the parabola. So I now have an axis of symmetry. I have a vertex. I have two symmetric points indicating how wide the parabola is. And if I connect the dots, knowing it's going to have my usual parabolic shape, I can then finish the graph of this parabola. Please note you must label the parabola with the equation that generates it. Alright, so nice three-step system, axis of symmetry, vertex, and two symmetric points In this case, it was the X-intercepts. Okay? Let's do another example. If I ask us to graph a parabola that looks something like this, well, as we know, if the lead coefficient is negative, it's going to be concave down. So it's going to look like possibly like this, possibly like this. The determination of symmetric points will give me an idea of how wide or narrow this parabola is. Okay? Alright, so we can expect, just from an inspection on the very first glance, we know it's going to be a concave down parabola. So let me write it down here again. Graph y equals minus x squared plus 4x plus 12. Alright, step 1. Find the axis of symmetry. Well, that's going to be determined by the equation x equals minus b over 2 times a. X equals minus 4 over minus 2. Well, that's positive 2, is it not? So the axis of symmetry is the vertical line x equals 2. Let me rewrite that because I'm going to need the room to do other work. So I'll put that down. Axis of symmetry is the vertical line x equals positive 2. Let me go ahead and graph that. I'll do the best I can here. Doesn't look too bad. Alright, so x equals positive 2. And let me do that in a different color. And of course represents the vertical line about which the parabola has vertical symmetry. Okay? Alright. Oops, forgot to label the axis of symmetry. Let me label it down here because the parabola is going to be concave down. So I'll put the label of the axis of symmetry down there below. X equals 2 is the axis of symmetry. Now the vertex. Step 2. As we know, the vertex occurs on the axis of symmetry. That means the x-coordinate must be 2 on the vertex, right? What's the y-coordinate going to be? Well, I'll plug in x equals 2 into the above equation and solve for the missing y-coordinate of the vertex. So y equals minus 2 squared plus 4 times 2 plus 12. So minus 2 squared is going to be negative 4, plus 8 is 4, plus 12 is 16. So the y-coordinate of the vertex is positive 16. Let me go ahead and erase this work and rewrite that for the sake of space. When x is 2, y is 16 on this vertex. And I'll graph it. I'll put it up here somewhere. When x is 2, y is 16, that is going to be my vertex. Alright, again, we don't know how wide or narrow this thing is going to be, so I'll establish 2 symmetric points, and how you do that depends on the problem. I suspect I'm going to find the x-intercepts here. Right? We'll talk about a case where the x-intercepts don't exist in a parabola. We'll do that in our next example. So I'm going to find the x-intercepts, and I do that like I did in the last example. Well, to find where you hit the x-axis, you set y equal to 0. So I'm going to let y equal to be 0 and solve the resulting equation for x. Alright, I've got a degree 2, a quadratic type equation. in standard form. I'm going to solve it by factoring, so I'm going to multiply through by -1 to get things a little more manageable. I can then break this down as to x, let's see, x plus 2 times x minus 6. I believe that works. The outer product is minus 6x, the inner product is plus 2x, and those indeed add up to a minus 4x. So I've got two x-intercepts at -2 or positive 6. So let me go ahead and graph those. When x is -2, y is 0, and when x is 6, y is 0. Alright, so I've got my two symmetric points. They're equally distant from the axis of symmetry, as you can see. And with those 3 points, I'm going to now graph my parabola. And along with the axis of symmetry and the vertex, and of course the two symmetric points, I've got a nice picture with all the action, and of course label the parabola with the equation that generates it. Equals -x squared plus 4x plus 12. Alright, let's do a case now where the x-intercepts are impossible to find because the parabola doesn't intersect the x-axis. There's a little trick to handle that situation. Get a fresh screen here, I might run out of room. Let's see. Let's graph this expression. Graph y equals x squared plus 4x plus 5. And I'll do my best to keep it in the same window here. Step 1. Find the axis of symmetry. Well, that's the vertical line. X equals minus b over 2a. Well, if b is 4 and a is 2, minus b over 2a is the vertical line. X equals -2. Alright, so let me go ahead and start graphing this. X equals -2. Puts me here. And let me go to a different color. Label the axis of symmetry, and we're ready to go on. Alright, step 2, find the vertex. Well, as we know, the vertex occurs on the axis of symmetry. Hence, the x-coordinate must be -2. What's the y-coordinate? Can we do this in our head? -2 squared is 4, plus 4 times -2 is -8, plus 5, that's going to be a +1. When x is -2, y is 1. Let me label that. Vertex is -2, 1. Well, let's talk about the symmetric points. Well, I think you'll agree with me, if this parabola, let me show you something here. If my vertex is at -2, 1, and if I have a concave up parabola, and I know it's concave up because my lead coefficient is positive, there will be no x-intercepts. I'm drawing this in green because I'm going to erase it quickly. No matter how fat or skinny this parabola turns out to be, there will be no place for it to hit the x-axis. Alright, so what are we going to do? We can't find our x-intercepts. There just aren't any. So I'm going to delete that. And let me note here, find two symmetric points. There's a little bit of a trick here. Two symmetric points. And again, there's no x-intercepts. So finding them is not going to work. Right? There just aren't any. So what I'm going to do is find the y-intercept because every parabola has a y-intercept. Every parabola will hit the y-axis somewhere, and then basically count squares to determine a second symmetric point at that same y level. Show you what I'm talking about here. If I look at my original equation, I can find where this parabola is going to intersect the y-axis. If I let x be 0 and solve for y, that will be the y-intercept. Alright, so let me see if I can squeeze this in. I guess I'm going to have to scroll down a little bit. Let me copy down the equation first. If I let x be 0 and solve for y, well, that's easy to solve. If x is 0, that means y equals 5. So my parabola is going to intersect the y-axis at the coordinate 0, 5. So I can graph that. 1, 2, 3, 4, 5. Right here. When x is 0, y is 5. That's where the parabola is going to hit the y-axis. Now you'll notice there are 2 units of distance between the y-intercept and the axis of symmetry. That means if I count over 2 more units to the left, I should have another point on this parabola. Now the y-coordinate is going to be the same because we're at the same y level. This x-coordinate is going to be -4, 2 units left of the axis of symmetry. So I can establish, with a little detective work, 2 symmetric points at the level y equals 5. Alright, so with my axis of symmetry, with my vertex, with my 2 symmetric points, and a little detective work, I can then connect the dots and graph my parabola, of course labeling the parabola equation. Okay? Alright, so nice, concise system to graph parabolas. That concludes section 8.4, graphing quadratic functions, or quadratic functions and their graphs as stated in the book. That is all.